Hello students, my name is Shashank Shekhar and today is the third lecture of the chapter Alcohol, Phenols and Ether. So in the previous class, we have seen the chemical properties of this alcohol. Today we will discuss about the preparation that are used for the making of phenols. So if you look at the syllabus here, so we have covered alcohols, nomenclature, methods of preparation, physical properties. Today we will see it. Okay, so regarding physical properties, today we will see all the physical properties of alcohol and phenols and ether at once, so that we can make a good comparison of all of that. After that, we have seen chemical properties. Okay, right, and we have seen the reactions that can be used for the identification of primary, secondary, and tertiary alcohol. Now, yes, this one is also completed. That is mechanism of hydration, uses with special reference to methanol and ethanol. Today we will be seeing phenols, methods of preparation. Nomenclature was already covered in the first class along with the nomenclature of alcohols. Plus, we will also look at the physical properties of this phenols and the physical properties of ether. So if I look at the topics that are to be covered, so that are mainly about the preparation of phenol from chlorobenzene, from benzene sulfonic acid, from diazonium salt, from cumene. Then we will compare physical properties of alcohol, phenol, and ether at once, and then we will take a illustration of this boiling point. So starting with the preparation of phenol, as I have mentioned, so phenol was also called as carbolic acid. So it is also termed as carbolic acid, and it was first isolated in the early 19th century from coal tar. Nowadays, phenol is commercially produced synthetically. In the laboratory, phenols are prepared from benzene derivative by any of the following methods. So the methods, the substrates are haloarenes, benzene sulfonic acid, diazonium salt, and cumene. So we will see what this cumene is. Haloarene, you know it very well. It is nothing but halogen attached to a aryl ring. Benzene sulfonic acid means benzene attached to a sulfonic group. Diazonium salt, we have seen the preparation of diazonium salt in the previous class from this haloarene. Yeah. And the structure of cumene, we will see it later, but let me make just a picture of it. So it looks like this. Right. So this is cumene. Here H is attached and other two groups are methyl. So the first is preparation from chlorobenzene. So we will use this chlorobenzene. This is the haloarene that we are using, and we do it the nucleophilic substitution. So we know that nucleophilic substitution of this benzene ring is not possible because of several reasons. These reasons I have mentioned earlier, so I will just tell again about it. First of all, due to this strong Cl bond, since upon resonance, so if you do the resonance of this Cl, this will create a partial double bond. If this lone pair this delocalized over the ring, it will create a partial double bond between carbon and chlorine. Now due to this reason, there is a kind of strong bonding, and it will stop the say our bond breaking of C and Cl. Okay, now but it is possible due to some reasons. Uh, this harsh condition, first of all, 620 through 23 Kelvin and 300 atm pressure. Now if you look at SN1 and SN2 mechanism, suppose, so if you take suppose SN1 here, what do we take? We take the SN1 here. So for SN1, carbocation has to be formed. So this will result in a phenyl cation, and phenyl cation is not stable because it destroys the aromaticity. So if a phenyl cation will look like this. So this would be the structure of phenyl cation. Now due to this phenyl positive charge, the aromaticity of this benzene ring has been destroyed. Now suppose if we take the SN2, So if you have seen this benzene, so it has a cloud of pi electron, both above and below. It has a cloud of pi electron. Now, nucleophilic attack requires the attack of a negative charge on the nucleus or the positive charge. But since this benzene ring is surrounded on both sides by a negative cloud charge, okay. So this this pi electron is delocalized over all carbon. This creates a cloud of negative charge. So the incoming nucleophile has to face a greater repulsion from this cloud. Now, due to these three reasons, first, the carbon and Cl, the bond between carbon and Cl is of somewhat double bond character. Second, the instability of your phenyl cation, and third, the repulsion from the cloud, electron cloud. These three reasons avoids your nucleophilic substitution of your any chloro, or you can say any benzene derivative. But at the same time, if we use a harsh condition, so here you can see it is 623 Kelvin. So if you want to imagine how high this pressure is, you must know that, okay, the pressure that we are facing right now is 1 atm. So 1 atmospheric pressure is right now the atmospheric pressure around you. So it is 300 times greater. That pressure we have to create must be 300 times greater than the atmospheric pressure. It is like something it is put up in a ocean. So down deep down the ocean, the pressure is high. Plus 623 Kelvin. So now, so your current temperature right now would be 300 Kelvin. It is double that temperature. So it would be very high temperature and high pressure. So in that case, it would result in a sodium ethoxide ion. Why sodium ethoxide ion? Why not phenol? Since it has a OH as a nucleophile, why it is not replacing the chlorine and introducing OH here? Because since this NaOH is also a base, so it deprotonates this phenol and result in this kind of species. Okay, clear? So this is the mechanism. So it goes through nucleophilic substitution under harsh condition. Further, this sodium phenoxide, this sodium phenoxide ion is later on protonated using your HCl. So HCl is the acid. So we introduce HCl here. So we will get this phenol plus NaCl. Clear? So this is the first method that can be used for the preparation of your phenol from chlorobenzene. Next is from the benzene sulfonic acid. So in this method, benzene is sulfonated using your this H2SO4 plus SO3. This is called oleum. So if you react H2SO4 and SO3, you will get oleum. So I will show you later on the structure of oleum. But for now, take it as it is something which can undergo electrophilic aromatic substitution. Now this oleum reacts with your benzene to give your sulfonated benzene. So this is our sulfonated benzene. So this first step is electrophilic aromatic substitution. Now again, the second step is again a nucleophilic substitution. What it is? A nucleophilic substitution. So we have to treat it with NaOH. But since this SO3H is a good leaving group, so this facilitates your nucleophilic substitution and it occurs under normal conditions. Further, you protonate that again, that's sodium phenoxide with H plus, and you get back your phenol. So the processes are same. So only one step is increased. Here we have done first the electrophilic aromatic substitution. So if you take the chlorobenzene also, you can just extend this one more step. This step you can extend it also. First you chlorinate it using your dark and FeCl3 and Cl2. Then you just the electrophilic aromatic substitution. After electrophilic aromatic substitution, you will get chlorobenzene. Then you introduce NaOH under high temperature and pressure. And second, you will have to protonate it. Clear? So this is the thing. So it is written here also. The benzene sulfonic acid so formed is converted into sodium phenoxide on heating with molten sodium hydroxide. So it is also done at high temperature, but not high pressure, but high temperature. See, it is written that it is converted to sodium phenoxide on heating with sodium hydroxide, molten. Okay, heating with molten sodium hydroxide. So you have to heat it. And acidification of the sodium salt gives your phenol. So these are the two ways. The first one is from the chlorobenzene, and second one is the benzene sulfonic acid. So both of this kind of follow the same mechanism. You can see that first it goes your nucleophilic addition and then you protonate it. Okay, is this clear? So this is the thing. Now we will move to diazotization. Before that, let us see the structure of oleum. So oleum looks like this. So this is the structure of oleum. Now you can see that this bond is very weak. Okay, these two bonds are very weak. They can be easily broken. So there's a nucleophile. This nucleophile attacks here and it removes this group, and you get back your SO3H, which is this SO1, O2, O3, and H. So this is the structure of oleum. So let me light it properly for you. So it looks like this. So this is oleum. And how it is formed? It is formed by the reaction of H2SO4 and SO3. Clear? Okay. Now next, from diazonium salt. So those who are not aware about the previous chapter lectures, so there we have used our aniline. This is the aniline that we have. It is also called, it can also write it as amine benzene or amine phenyl, anything. But the common name that is used is termed as aniline. 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 Now our diazonium salt is formed. So this is our diazonium salt. It is a salt. So when you call a compound as salt, so when it has a type of ionic distribution, plus and minus. So like we have K plus and Cl minus, you call it as salt. Or you can have, say, this sodium phenoxide you have seen earlier. That was also an example of salt. Okay. So this kind of structures are called salt. So it is benzene and diazonium salt. So this is diazonium chloride. Okay. Now this benzene diazonium chloride is formed by treatment of aromatic primary amine. So this one aniline is an aromatic, since this contains aromatic ring. Primary amine because it is attached to one carbon only, with nitrous acid, NaNO2 and HCl at 0 to 5 degrees Celsius or 273 to 278 Kelvin. So you treat this thing. Now diazonium salt are hydrolyzed. So if you hydrolyze it in presence of H2O and warm water, simply add H2O and warm water. Then heating it with warm water or by treating with dilute acids also. Sorry for this. So if you treat it with suppose you treat it with dilute H2SO4, this thing, then you will also get this OH. Now what is the driving force here in this reaction? Why upon addition of just warm water gives the phenol? Release of this N2 gas. Now on this side the anisotropy is increasing because gas has a greater anisotropy. Therefore this increase in anisotropy, so the two products are gaseous here. So this HCl is also formed as gas and this N2 is also formed as gas. So the formation of two gases increases the delta S. So it makes it positive. So due to this increase in anisotropy, this reaction is facilitated. Now the driving force in the second step is release of nitrogen gas. The same thing is written here. Okay, this is clear. So this is from the diazonium salt. Next, from cumene. Okay, this is from cumene. So this thing I mentioned earlier also, this is called cumene. Now what do? We first take cumene and it is oxidized in the presence of air to cumene hyperoxide. Now this conversion from here to here, this is a kind of following the radical mechanism. So the mechanism I will show you in the next slide. But for now, take it as like the insertion of this O2 between C and H bond. So it is C and H bond here. So this O2 is inserted between both of these, and it is a kind of oxidative insertion. We are inserting something, and that is doing the oxidation of this compound because we are adding oxygen, which this results in the formation of cumene hyperperoxide. So why is this word hyperperoxide used? So anything which has a OO double like this single bond and something attached on both sides, this is termed as hyperperoxide. So we have an example of this also, H2O2. Okay, hydrogen peroxide. So it is hydroperoxide. Okay, this is hydroperoxide, and this is called hydrogen peroxide. So this oxygen single bond is the reason why it is termed as peroxide, right? Then it is further hydrolyzed to get OH. Clear? Now, how does this mechanism goes? How do we get this thing from here to here? First, we will look at this. So this one more thing I have to mention here is that most of the worldwide population of phenol is done from cumene. So this is an industrial method. So if you want to generate phenol on industrial scale, then you must use this method. Now acetone is released as the byproduct. So you can see clearly that acetone is released as the byproduct. And this it is convert, and this is obtained at large quantity. So in this case, we get large quantity of your phenol. So let us see the mechanism first of all. How does this go? So it goes through a radical mechanism. So I put up a picture of the mechanism. First of all, where are we here? So we are here cumene, and we have radical R. So we will see where this radical is coming from and why is this radical stable. Okay, so there are two ways this radical can be formed. First, that this H gate removed, there occurs a homolytic cleavage of this H and C bond, this bond, homolytic cleavage of this bond. This would result in R radical. So this thing is termed as R radical. So this is the R radical here. And why is it stable? Because it is kind of being resonated throughout the ring. So it is stabilized by phenyl. First of all, this radical is formed. Now what does this radical does? Or we can take any radical. Now this radical takes one hydrogen from here. Okay. Second, this oxygen also gets homolytically cleaved. So it has a double bond. So one of this bond goes here, one of this bond goes here, and we get this species, which is this one. Now this radical and this radical will combine and result in this kind of species, and this will again extract one proton from the starting one. Okay, and this will generate our this thing again. Clear? And we got this thing, that is cumene hydroperoxide. Clear? So this is the mechanism for the change of cumene to cumene hyperperoxide. Now what we have done, we have hydrolyzed it. So how do we hydrolyze it? How can we hydrolyze it? Very simple. So this is our cumene. Let me draw it properly for you. Sorry. So we have OOH and we have CH3 and CH3. First of all, what will happen? This will get protonated. Okay, so since we are doing it in presence of acid, it will get protonated. Clear? So since it is protonated, this will leave in the form of OH2, and we will get this thing here. This is our CH3. This is again our CH3, and we have now a positive charge on O. Now the H2O that has been formed, it will attack here. This will go here. Clear? So what it will result in? So let me draw it for clearly for you here. So it will result in kind of O H H positive plus CH3 CH3. Now again this proton will be abstracted. So since it is an acid catalyzed reaction, you will get your H back. And finally the phenol will be formed as the final product. So in this way, it is further hydrolyzed. This thing is further hydrolyzed to your phenol. First, this gets protonated and this leaves, and the H2O then formed is attacking here, and we got our acetone plus H2O attached to this benzene ring. Now, since it is an acid catalyzed reaction, we have introduced one H plus on this. So this H plus will be again released by your protonated oxygen. Clear? So this is the way in which cumin is used for the preparation of phenol. Next, now let us move to physical properties. So in physical properties, we will discuss about two things. First is your boiling point, and second is your, say this is a solubility. So boiling point is kind of dependent upon the intramolecular hydrogen bonding. So boiling point increases with increasing number of carbon atom because of van der Waals force. So you know this, that boiling points increases because increase in the number of carbon atom. Now branching decreases van der Waals forces due to decrease in surface area. So I've mentioned it earlier also. So if you take something linear, that would occupy more surface area rather than something which is circular of the same chain length. Now one very good comparison is given here, that the boiling point of alcohol is higher with comparison to hydrocarbon, ether, haloalkane and haloarine. So all of these have a lower boiling point than alcohol. That is hydrocarbon, simple hydrocarbon, ethers, haloalkanes and haloarine. And why is it so? It is simply due to your hydrogen bonding that is present in case of alcohol. Ether, since ether is polar, so it is kind of having a higher boiling point as compared to simple hydrocarbon, but it is not higher than the alcohol because it is kind of having hydrogen bonding. Now solubility, if you talk about solubility, the solubility of alcohol and phenol is higher due to their ability to form hydrogen bonds. So you can see here, so here is an alcohol. Okay, this is an alcohol and it has formed hydrogen bond with 3 water molecules. Okay, sorry, it has formed hydrogen bond with 3 water molecules, this oxygen. Okay, so 2 are being attached to this oxygen and 1 is being attached to the hydrogen of your alcohol. Due to this, the solubility increases, but the solubility decreases with increase in the size of alkyl aryl group. Why is it so? That if you increase this chain length, the solubility decreases. Now you know it very well that okay, this is this thing here is being kind of introduced due to the polarity of this bond. But as we introduce this CH3 group, this will decrease the polarity. Okay, this will decrease the polarity of this OH bond and hence the solubility will decrease. The solubility decreases with increase of alkyl or allyl group. Now several of the lower molecular masses are miscible with water in all proper proportions. Due to this decrease in, say, dipole moment on increase in the chain length, you can say that the lower molecules, the molecular mass, the alcohol having the lower molecular mass are being easily dissolved in water as compared to the one which are having the greater molecular mass. So this is the comparison of what we have: ethanol, methoxymethane and propane. Now all of these three are having comparable masses. What they're having comparable molecular masses, because why have we done so that the van der Waals could not affect the boiling point. So we have kept all of this at least so means having the almost same molecular mass. So if you look at the molecular mass, this is having 46. Molecular mass is 46. It is also 46 and it is 44. So you can see that all of three have a comparable molecular mass. Now ethanol and propane have comparable molecular mass, but their boiling point differ widely. So this is 46, ethanol and propane. You can see that it has a molecular, say boiling point of 351, and it has a boiling point of 231. So what is the reason behind this? The reason behind is very simple. It is due to hydrogen bonding that is present in case of ethanol. But this hydrogen, this cannot form hydrogen bonding. So let me make a point here. Only the hydrogen that is connected to oxygen or fluorine or sometimes chlorine or nitrogen. I would not consider chlorine also. So nitrogen, oxygen, fluorine. So if a hydrogen is attached to all of these three, then and then only that hydrogen is capable of doing the hydrogen bonding. So is this clear? So I am telling the point here is that if your hydrogen is attached to nitrogen, oxygen and fluorine, then and then only that hydrogen will be capable of forming the hydrogen bond. But here you can see it that this hydrogen is attached to carbon. Okay, and this whole hydrogen bonding concept is critically based on the electronegativity, and carbon is not that much electronegative to support your hydrogen bonding. Now due to this reason, this propane hydrogen cannot do hydrogen bonding and its boiling point is low. So this is the reason. Now if you compare it with this ether, so this ether has kind of is in the intermediate. So this is in the intermediate of alcohol and propane. Now why has it introduced some kind of say strong boiling point? So why it is a higher boiling point? Sorry. So why it is a higher boiling point? Because it has kind of say polarity. So how does it happen? So let's think it like this: that this electron clouds are of course being distributed among the different atoms, but these electron clouds are not exactly positioned at one place. They do say kind of they do rotate here and there. Okay, or you can say they do get delocalized here and there, but the delocalization is such that the electron distribution is well according to the electronegativity. But there occurs a condition at some time that this electron density for a small instantaneous time, suppose for a time that is approximately equals to 0, delta t tends to 0, for that time your oxygen or your the polarity is increased. Okay, right here. So in this case, which is already a symmetrical one, but instead it has a polarity. Why? Because this has a direction here, it has a direction here, so this will result in this direction. So it is kind of opposite. It goes from positive to negative. So this dipole moment is in this direction and this one is in this direction. So if you just open it, or you can say resolve it, then since this and this are in the opposite side, so let me draw it properly for you. So this is the structure of your ether that I have given. Now for the students who are unaware about the dipole moment, so dipole moment goes from positive to negative direction. Okay, similarly, so why is it positive? Because it is carrying a delta positive charge, that is as it is less electronegative. So it is delta positive, and it is delta negative. Here also the dipole moment direction goes from here to here. Now what we know about the resolution of vector. So we can resolve it along the axis. Suppose this is our x-axis, y-axis. So what do? So this is suppose this is our y-axis and this is our x-axis. So we resolve it. So after resolution in the two directions, you will get this thing and this thing. Similarly, if you resolve it along two axes, you will get this kind. Now since this one and this one, they are in the opposite direction, and since they are coming from the same set of molecules, that is OCH3 and OCH3, so this both will be cancelled out. Okay, it will be cancelled out, and one of this resolved vectors is having the same direction, so they will add up and result in some polarity. Okay, So that would introduce some polarity to this OCH3 CH3O. Now, due to polarity, there is a dipole-dipole interaction between two such molecules. Okay, if you take it like this, so this is our OCH3, OCH3. So this is a delta negative charge, and the CH, this will have a delta positive charge. Okay, clear? So this kind of interaction that has been seen here, this kind of interaction is being set up between two ether. Okay, clear? So due to this reason, so above, say, in addition to this van der Waals forces, ether have a dipole-dipole interaction. Due to this reason, its boiling point is higher. Okay, its boiling point is higher than the normal hydrocarbon. Now what happens if we compare it with the haloalkane or haloarine? So now this haloalkane or haloarine will not have hydrogen bonding, of course, because there is no say hydrogen attached to this halogen compound. There is no hydrogen attached to this halogen compound. But the polarity of this say electronegative halogen and carbon is much more as compared to ether, because there is no cancellation of the resolved vectors. Example, if you take like this, so this will have only one dipole moment in this direction. So this dipole moment, this magnitude of dipole moment will be more in case of your CH3Cl, and it will easily form bonding with another molecule. And due to greater polarity, this interaction will be of higher magnitude. Clear? So this will be of a higher magnitude. Therefore, if we compare all of these, I can write here that if we have comparable mass, so the statement should be clear, the masses should be comparable, so that the effect of van der Waals force or the effect of van der Waals cannot disturb the boiling point. So if all of these have a comparable molecular mass, then we can say that alcohol have the highest boiling point. Then we have halogen, okay, halogen containing compound. Okay, and then we have ether, and then we have this hydrocarbon. But for whom? For comparable molecular mass. Clear? So this is our boiling point. So for now, I would treat this as a good end point for the lecture to end, because you can now think over it, this series, and of course you can do some questions accordingly, so that it can make your concept more clear. So try some questions, try some physical properties question. Okay. So thank you. So for in the next class, so before ending this lecture, in the next class we will discuss about this phenols reactions. So we have not seen the chemical reactivity of this phenol. So we will see the acidity. So what kind of acidity this phenols hold. So we will see all those things in the next class. So thank you for your time. With this, I will end my lecture.